Thank you all for coming to the NLI SJSU event with Professor Chris Potts today. Professor Chris Potts is a professor at Stanford University, and he commuted all the way here through rush hour traffic just to present to you guys. So you guys are in for a treat. Chris is one of the most awesome, supportive people that I know. Now, also, if you signed up for the dinner afterwards, we will be going out to dinner together so you get a chance to get to know Chris Potts a little more personally. And yeah, it'll be great. So let's give a big round of applause for Professor Chris Potts.
Thank you, Andrew. I'm glad to be here. If you travel in the sort of Twitter circles that I do, or if you follow the popular press about AI these days, you often hear that tasks have been solved. I've put solved in scare quotes. I want mainly to offer some nuance about what people mean when they say tasks have been solved and how sometimes that message gets distorted. I'm going to be focusing on NLP, which is my field, but I think that these general patterns of reporting and discussion and the underlying results that we're all talking about kind of hold throughout artificial intelligence research at this point. I gave this talk this summer. Andrew was there, to the Stanford students, and I think I was accused of sort of being an anti-technologist because I guess I'm trying to be a realist, but that could sound pessimistic. So I do just want to acknowledge that we do kind of live in a golden age of artificial intelligence. Lots of amazing things have happened. You know, just in the span of my career, stuff that I thought would be science fiction is now reality. So like maybe you guys trust having these devices in your homes. There's a lot that's impressive about them, but I might home in on just the fact that they can do such good speech-to-text transcription. I mean, 15, 20 years ago, the level of accuracy that they achieved was unheard of, and now it's pretty good. The intention recognition part is maybe less good. I work in natural language understanding, and I think it's still a wide open field. But still, lots of progress, and we get utility out of these things. Another thing that would have seemed like science fiction 10 years ago is the way Google Translate and other large-scale translation systems can function. So they can deal with dozens or hundreds of languages, and the level of accuracy that they achieve is often really spooky. Here is just an example. I've given an English text on the left. There's its French version on the right. And its French version is really close to the human standard translation for this example. There's the standard thing about it differing kind of on some prepositions and some stylistic stuff, but by and large, it's a very impressive translation. And again, just retreating to the fact that even if it's not perfect, it's incredibly useful in your lives. And again, 15, 20 years ago, it was not at all obvious that that was true. Image captioning, that's another very impressive place, a combination of NLP and computer vision. Here I've given some really nice captions, a person riding a motorcycle on a dirt road, a herd of elephants walking across a dry grass field, fluid text, accurate, a nice description of these pictures. Again, very impressive stuff. And if you live, we probably all live in these strange neighborhoods that have self-driving cars driving around in them. Again, I never would have guessed that in 2019, there were going to be self-driving cars around, and it's a triumph of data and compute power and scientific innovation and everything else, so it's all very exciting. However, if you're a practitioner, you can kind of put these things into perspective. So let's do a peek behind the curtain here, and I've got a picture of Blade Runner, right? This is a case where you interrogate the replicants in a kind of Turing test, and it's eventually revealed that they're not human-like. Those are pretty sophisticated interviews. Of course, the stuff that we have to do to break these AI systems is nothing like that. This is Google Translate, which I was just saying is amazing. Someone has just randomly inputted a bunch of vowel sequences. Google Translate has guessed that this is Hawaiian, which is a kind of interesting guess about Hawaiian syllable structure. And then the scary thing is that there's some fluent text on the right. It has nothing to do with the input. A minor change to the input will cause a radical change to the output. And you start to see that these things aren't intelligent in any meaningful sense. I hid the captions to the right of this first panel from you before. This is from a groundbreaking computer vision paper for image captioning. I showed you these, but if you go all the way over to the right, you have things like a dog is jumping to catch a frisbee, but there's just a dog standing next to a woman there. Or I like the one on the bottom, a yellow school bus parked in a parking lot. It's not even really close. And they are, in fairness, describing this as without errors all the way up to, what does it say, unrelated to the image. So not the sort of thing a human would do, exposing some cracks in these technologies. You might have seen these experiments in adversarial probing of networks. I'm going to return to that in the NLP context. But just briefly, the story is, okay, I've got a model that does a good job of identifying this as a panda, but if an adversary adds some noise to the image, and the noise is calculated based on the model parameters, first of all, it thinks that that noise is a nematode. I'm not sure I could identify a nematode, so maybe that's okay. But then this picture plus that nematode, visually not different to us from the original input, but now it's 99.3% confident that it's a given. That's kind of an interesting thing in and of itself, and all these things are ground truth, but in fact it's just been curated in some automatic fashion from the web. And this is a funny one here, that this kind of goes back to the original Siri. This is Stephen Colbert on his old show. The premise of this little skit is that he's gotten his iPhone and he's been playing it with all day, so he forgot to write his show, and he says, write the show to his phone, and Siri says, what would you like to search for? That's its standard out when it doesn't know what you want. They go on a little bit like that, and then it says, for the love of God, the cameras are on, give me something. And what Siri says in response is, what kind of place are you looking for, camera stores or churches? And I've done some color coding just to show you that a very brittle solution has been exposed here. It scanned for the word God, and it scanned for the word cameras, and it did its level best. But its level best is nothing like the dream of AI. So if you kind of put together all this stuff, the exciting stuff I open with, and all these cracks, you get kind of two perspectives. So on the one hand, this is a book by Nick Bostrom, philosopher, not a practitioner of AI, but certainly insightful. And here you have a worry that these artificial agents are going to become incredibly intelligent and take over the planet, and it's the end of humanity for all of us. That's one extreme position. That you might worry about when you look at my first set of pictures. You could counterbalance that against this lovely book by a practitioner or roboticist at Intel, How to Survive a Robot Uprising, which is full of advice like run up some stairs or wear a certain kind of clothing so that the vision system breaks down and it can't find you anymore, stuff like that. And the failures that I just showed you are much more along that dimension. So that kind of sets the stage. Lots of reasons to be optimistic, but lots of strange stuff showing that these systems are not intelligent in any meaningful sense. So let's zoom in, though, on NLP. Some natural language tasks are described as solved. You see this, as I said, on Twitter from practitioners all the way through the popular media. What is it really like when we say that they're solved? For the talk, I'm going to distinguish three kinds of solution that you might imagine. So the first one would be perfect performance in all environments. I have a feeling that sometimes, especially in the popular press, when people say solved, they're thinking of something like one. And for NLP, one is basically not on the table. So you might go down one level to 2 here, performance at or above humans in all or nearly all environments. Not perfect, but superhuman. And again, I think people have expectations that what it means to be superhuman is in all contexts where a human did something, the machine was as good or better. The third sense of solved is the one that I think practitioners mean if you press them. Performance at or above humans only in controlled environments with specific metrics. That's deflationary. That is not an exciting sense of solved, as I'm going to show you. But it's the one that we've achieved for a handful of tasks in NLP. Just to give you a sense for what these different levels of performance would be like, let's start with perfect performance. We do have some recent instances of this in AI. They happen to come from game solving. So a breakout result from about 10 years ago is that checkers is solved. And it's solved in the sense that they have a way of exhaustively exploring the entire game tree of chess, and they can therefore play optimally in all scenarios. A perfect solution, unbeatable. It's the result of some AI stuff, some innovation around search, and massive compute power. And it took a few decades for them to achieve this result, even when they knew what the path was going to be. An amazing result. This is a slightly more nuanced version. So this one says heads up limit hold'em poker is solved. I don't have any idea what that means in terms of poker, I have to confess. I think it's a kind of easy version of poker. But I put it up here just to emphasize that this isn't quite perfect performance, because since poker is a game with some uncertainty and some partial information, you have bounds on how well you can actually perform. Within those bounds, which are kind of mathematical bounds on the game, it's solved. And they give some nuance in the article about how it's solved. But the bottom line is, that's a case where even under uncertainty, we have a essentially perfect solution now. Those are the ones that I could think of for perfection. And I think it's not an accident that they come from games, because they have tightly defined rules. We can program those rules in, and then the system can kind of operate within those bounds. Let's move to performance at or above humans in all or nearly all environments. This is a more interesting class of AI breakthroughs of recent days. This is an older one here. This is TD Gammon. It's a backgammon playing game from the early days of neural networks. And it finds heuristic solutions and in some sense is superhuman. It's not a solved version of backgammon, but it's a very good intuitive player of backgammon according to experts. And that was an exciting thing just because it was an early breakthrough of this kind of data-driven game-solving approach. In the middle you have Deep Blue. Deep Blue is a famous chess-playing game that I guess is as old as most of you now. The late 90s is when Garry Kasparov was beaten by Deep Blue. Certainly a breakthrough result of very impressive compute power. It's not solved because chess is so much more complicated than checkers that there's really no hope of exploring the entire game tree. But at that point, it was superhuman, and I would say that now, even devices that you might have on your laptop or your phone are superhuman in the sense that they can beat most or all of us, most or all of the time. I have AlphaGo there as well. That's a more recent thing. Some teams from Google built systems that are superhuman along some dimensions for the game of Go, and that's impressive because it's much more complicated than chess. There's really no hope of doing exploration of the game tree. Instead, this is a kind of triumph of game solutions combined with deep learning and lots of compute power. And the interesting thing about the AlphaGo solution, according to Go experts, is that like TD Gammon, it kind of plays in an intuitive way that doesn't match the things that humans do, and is not at all like Deep Blue's solution of just searching a game tree. And then I have up there in the corner, in the right there, the one that's the closest to NLP, which is the original IBM Watson system, which played on Jeopardy and famously beat Ken Jennings, who was the world's best Jeopardy player at the time. I'm going to return to Watson in a minute, but it's the closest I could come here to having an NLP solution on the slide. Oh yeah, I have my Watson examples here now. So Watson was very good in virtue of the fact that basically it had mined a lot of Wikipedia and discovered in a kind of rudimentary way how to do information retrieval in a way that was matched to the Jeopardy rules. And in addition, it had some really good stuff around how it would press the button, because reportedly a big part of Jeopardy is not just answering the questions, but being good with the button so that you get your chance to answer. So it was a kind of NLP system combined with a very custom game playing system. And I know of two examples that are kind of illuminating about how Watson was solving things. So the first is, you know how Jeopardy has things backwards. So the prompt is grasshoppers eat it, and you're supposed to give the question to that answer. And what Watson said is, what is kosher? It's a very non-human thing to do. Does anybody have an intuition about why Watson might have said, what is kosher in response to grasshoppers eat it?
Maybe when data mining could be dictionaries or, various things, culture would be something grasshoppers eat.
I suppose grasshoppers probably had their preferences to keep kosher, so that might be right. So that would make it a kind of true answer in some sense, not the intention of what or the eating, but it's not quite that, but you have the right intuition about the issue. It's something about scanning through data. Yeah?
Maybe related as something eating grasshoppers.
That's also very charitable. That's like saying it had a sophisticated parse that it got slightly wrong and therefore has the wrong direct object, right? These are close. I would say some combination of your two answers is the right answer.
Grasshoppers feed on culture or something like that?
Any other guesses? The right answer is that in Wikipedia, which Watson depended on heavily, there is an extensive discussion on the grasshoppers page about whether or not it's kosher to eat grasshoppers and other kinds of insects. Perfectly reasonable discussion, an edge case for those kosher rules. And as a result of doing kind of heuristic search of those web pages and seeing that strong association between these two concepts, it came up with an absurd answer to this question. This is a more subtle one that reveals how humans can be kind of deceived by these AI systems. So it says, Watson also tripped up on an Olympic oddities answer, but so imperceptibly that Alex Trebek didn't notice at first, raising an important point of clarification. After Jennings responded incorrectly that Olympian gymnast George Eisner was missing a hand, Watson responded, "What is a leg?" The subtlety there is that the right answer is what is missing a leg. And what Alex Trebek did was a very human thing of assuming that Watson's answer was kind of elliptical to the previous answer, missing a hand, so that he interpreted that as the speaker intending to say what is missing a leg. Very human thing to do. What he forgot is that Watson had no access to the discourse context. It couldn't hear what other people were saying. And once you realize that, you realize, well, it's not elliptical, it's not anaphoric to that previous utterance. This is just wrong. It's a kind of garbled answer because it's missing the crucial information about missing a leg. And that's kind of, I'm going to return to this theme. That's a case where we can imbue these systems with more intelligence that they have just by doing a very human thing of being charitable listeners. Other things that are kind of superhuman, undoubtedly, fraud detection. I picked this as one of many examples where the way that you can achieve superhuman performance is because you just have so much data and the patterns are so subtle that we have to admit that computers are better than us at that kind of thing than we are. So like here, the idea is that if you just scan through all these transactions trying to find the fraudulent ones, you'd probably fail at that in virtue of the fact that you have some wrong prior assumptions about what a fraud is, and maybe you would just lose track of where the information was expressed and what was unusual. Whereas that kind of pattern matching is the very definition of something that computers are good at this point, especially kind of with data-driven systems. This is another case, but this is a more controversial one. This is one where my thinking isn't yet settled about whether or not what we're observing here is superhuman performance. So this is a paper that appeared from a team at Google. It's a biomedical paper, and what they're doing is looking at risk factors for various conditions by observing lots of images. And they have supervised data, so for these images they have a bunch of labels essentially saying what's true of the underlying human that the image is of. And they have a bunch of categories that they look at. I'm not going to dive into the details of this, I just wanted to highlight one of the categories here, which is gender. And the interesting thing about the gender performance is that they report essentially perfect accuracy for their system, whereas humans, just looking at visual images of people's eyes, which is what the data are in that case, are essentially at chance. They say that they're exactly at chance in terms of guessing what they call gender, but I'm assuming it's the biological sex of the human who had that eye. So that sounds like superhuman performance, right? This is something that humans completely fail at because we're obviously not attuned to the relevant kind of information in those images. And nonetheless, this deep learning system has picked up on a pattern with near perfection. It's able to make these predictions. So that would be a case of superhuman performance for sure, but I do want to qualify that a little bit. So first of all, what I think we need to know about this result, whether biological sex is reliably expressed in the eyeball, whether there's an underlying biological basis for that. If there is, then maybe we could trust this result, at least initially. But if there isn't, if there's no obvious biomarker that a visual image would contain, then I think we start to move to the idea that this system has just overfit to a very small data set. It's just benefiting from things that are in the images, and it doesn't have a generalizable solution. That's a very common thing for computer vision systems to be susceptible to, and it would mean that this isn't really superhuman performance, but rather just a luck of the data that the system was exposed to. Yeah?
Has this particular result been exposed to like the adversarial noise as previously stated?
That's a great suggestion. The question was, has anybody done some adversarial testing of this solution? Not to my knowledge, but that would be a good way, using these techniques, to home in on whether or not it was benefiting from some artifacts of the images. Yeah, but the real question for me, which I don't have an answer to, is this even possible? That is, do human eyeballs from the visual images, so the information that in principle the system has, can we make a determination of biological sense? And this is a kind of common pattern when you read these results. You say like, oh, something is perfect or superhuman. We should always wonder whether we're seeing truly generalizable performance or whether we're seeing something that's just a fact about the data set and the training regime and the way that the system was evaluated. I picked this one. This one is kind of funny. I think this is arguably a case of superhuman performance. This is from some colleagues at Stanford. The title of the paper is "It's Not You, It's Me, Detecting Flirting and Its Misperception in Speed Dates." Okay, so over here, accuracy of human listeners at labeling speakers as flirting or not. Male speaker, female perceiver. Women are more accurate than men, than the reverse here. Maybe that's not a surprise. I guess the old thing is that men always think they're being flirted with when they aren't. So that's the human performance. I should say that the underlying data for this is an actual speed dating event that Dan Jurafsky and Dan McFarland conducted at Stanford. People wore microphones, they had a lot of speed dates, and they filled out lots of survey information about each other after those speed dates. And the flirting information is coming from those post-date surveys. The systems that they trained, which had access to a lot of acoustic features and a lot of textual data, they're more accurate than the humans. And it's like, if you just look down here, by male, higher, by female, higher. So this is a case where the systems that they trained are apparently superhuman at detecting whether the speaker is being flirtatious with the listener. You could take that result with a grain of salt, but I think it's kind of amusing that there might be some cues in the speech signal and in the lexical patterns that a system is able to detect and that humans are kind of not as attuned to. But again, we should ask whether this is an artifact of the data or whether this is truly a generalizable capability. This is another more interesting case where I think we arguably see some superhuman performance from current day systems. And this is the phenomenon of stylistic accommodation. So the underlying generalization here is that when we communicate with each other, we do a whole lot of matching of each other's styles, from posture, head nodding, function word rates, the rate of speech, pitch, all these low-level things, on up to things like concept naming. So the words that you would pick to name complicated concepts. You'll kind of adjust each other's patterns and preferences so that you align. And probably the fundamental thing here is that all these acts of stylistic accommodation make it easier for us to communicate with each other. We don't necessarily have to agree in our real world goals to kind of stylistically accommodate. We do though just have to have an incentive to communicate with each other. And then all of these things emerge. There's a really robust literature on this. And now that I've mentioned it, you'll notice that if you're in a group of people talking, you'll feel embarrassed that all of a sudden you notice that all of you have crossed your arms at the same time, or you're all leaning back in your chairs in the same way. This is a kind of one noticeable example of stylistic accommodation. So a really interesting cognitive phenomenon, and the striking thing about it is that a lot of the stuff that I mentioned, like function word rates, speech pitch, these things are not really accessible to us in the sense that we're not consciously adjusting our rates of those things in order to accommodate. It happens as at a kind of more fundamental level. And even the concept naming thing, you might slip into it without really reflecting on why or even that you've done it. So humans observing behavior or monitoring their own behavior are not good at detecting when this is happening. But of course, we can write computer programs that are really good at accumulating the kind of statistical information that shows us that this is happening. And so that's a sense in which a computer can be superhuman in identifying the nature of the current accommodation. That's kind of like the fraud detection one in the sense that clearly we're benefiting from having zoomed in on some patterns that are really kind of high-level aggregate statistical patterns. And that's just the kind of thing that humans are bad at detecting. And then just to round this out, I picked out some other NLP tasks that are kind of in this neighborhood. I wish these lists were longer. This is the best I could do. Over here under straightforwardly superhuman, I put spell check, just because I think if I was worried about spelling mistakes in a long document I had created, I'd be better off relying on my computer than any one of you, sorry about that, to find those spelling errors, no matter how good you are at spelling, just because of the nature of the task. Although I should say there's nuance around all these things, and of course spell check kind of needs to be monitored by a human when it's automatic. There are lots of mistakes that a human could prevent, and those mistakes tend to come from linguistic context and so forth, making it unclear which change should be made, if any. Keyword-based search, like on Google, I think that's clearly a case where you're better off relying on a search engine than you are a human to find information in large collections of documents. Again, that's a kind of triumph of computers being fast at a certain kind of operation that people are pretty bad at. And then language identification, that's more or less truly a solved NLP task in the sense that with a modest amount of data and a pretty good modern model, you can do language identification with very high accuracy. Susceptible, I'm sure, to adversarial examples. I showed you that one before from Hawaiian, where the Google Translate had done a very poor job of language identification on random vowel sequences that somebody put into Google Translate. And we as humans recognize that right away. But nonetheless, on the whole, you can trivially train a system that could identify lots and lots of languages way beyond what any of us could do. So those are more or less straightforwardly superhuman. Superhuman in specific senses, I put over there grammar check, machine translation, and authorship detection. Again, these should be more controversial, but it's kind of like, if I'm not a native speaker of the language where I need to check my writing, a grammar checker is going to be a very useful tool. And in that sense, it could be superhuman relative to my abilities. If I'm a native speaker and an expert writer in the language, then probably I'll outdo the grammar checker, which is maybe unlike the spell check case. Machine translation, again, that's kind of nuanced. I showed you before Google Translate kind of fluently translating dozens or hundreds of languages back and forth between, right? That's something that no human can do. And that's, again, it's scale along a certain dimension that just outpaces what any human could achieve. That is not to say, though, that if you were, for example, born a bilingual in 2 languages, you're going to be vastly better than Google Translate at translating between the 2 of them. You'll do nuanced things that no system can do at this point. But still, superhuman along that one particular dimension. And then finally, authorship detection is an interesting one. It's not that we're even very good at this point at doing authorship detection as an NLP task. However, because authorship detection is kind of like stylistic accommodation, it's a game of observing low-level statistical regularities. These systems are often better than humans at identifying authors. Humans do the thing of thinking, well, I'll look for distinctive vocabulary items or other things that are really part of the observable style of this human, when in fact authorship detection succeeds in large part because of frequency of commas and idiosyncratic punctuation. Things that humans don't really notice or think is important, but nonetheless give those humans away as the author.
Yeah, can you go over number 3, authorship detection? I'm not quite sure what exactly is that.
So as an NLP task, if I wanted to just explore this, I could give you a bunch of novels from Project Gutenberg by various authors and train a classifier to identify for a new text who its author was.
Okay.
That would be kind of the low stakes way. You could just do that as a class project, but it would be on up to who is the whistleblower in the current Trump investigation or the preceding one, or whenever there's that kind of big thing that happens where an anonymous text appears, we might want to do authorship identification.
So it could be also used in plagiarism detection?
Sure, yeah.
Thank you.
That's probably another instance like authorship detection. Just because of the burden of memory, if I was gonna give you an essay and say, find in this other large corpus whether or not there's one that it plagiarized, that would be an incredibly demanding thing for you, whereas a computer can churn through and just look for some superficial patterns. Are there any others that you can think of that might belong in either column on this slide? Straightforwardly superhuman or superhuman in specific senses? Yeah?
Is the search function, on a lot of the websites could be part of this, like retrieving the like sentiment analysis or whatever it is.
Yeah, that's kind of what I mean by this. Yeah, I think that's straightforwardly superhuman.
Oh right, okay.
Yeah, and I mean, it could go beyond just keywords. I think just in general, information retrieval is a triumph of data and compute and some artificial intelligence stuff, straightforwardly better than humans. Yeah.
I was wondering how you would put autocomplete as a natural language in which column, probably, because there are some pretty good, like Google's pretty good at autocompletion, but then there are a lot of internet memes where you type in one word and it starts suggesting really crazy words, and then I feel like a random sentence using it. So yeah, I was wondering what you thought about
It's an interesting one, yeah, autocomplete. It's not so crisply defined as a task. I guess it would come down at this point to do you ever have autocomplete suggestions that you feel outstrip what you would have done as an author, that more perfectly capture your intention for this message than you yourself would have if you'd just been left unencumbered? That would be one way you could measure this. I guess the other would just be how often are people saying, yes, that's fine, and what are the speed gains? It's probably on its way to being superhuman, and that might cause some dilemmas, right? Because maybe we can all just type a few words and then watch our essays appear. Yeah.
I think sentiment analysis would be superhuman in specific senses.
Oh yeah, that's an interesting one, sentiment analysis. Maybe so I would say that would come down to, if it's really just a matter of scale, I'm going to give you 1 million documents and I want to know what the sentiment breakdown is, then of course that's a case where we can rely on the technology. That's a little bit like Google Translate, where I'm willing to compromise on quality because of the scale that I want to do this thing at. On the other hand, with just a few examples, and I do this in my courses on natural language understanding, just a few examples I could convince you that humans are way better than any machine. The amount of nuance, basically my pitch would be, in the limit, sentiment analysis is kind of AI complete. Is that a term people have heard? AI complete in the sense that having a perfect solution to that would imply having a perfect solution to all the problems of AI. Just because we can always go deeper and look for perspective shift and non-literal language use and other things like that. Andrew?
I have a suggestion for the superhuman in specific senses. So fake reviews online. People have a tendency to believe that it's a real person because when they see a name that sounds realistic, they'll be like, oh, that's a real person. But then a machine doesn't have those type of biases, and they can really extract whether it's a fake review.
Oh yeah, that's another interesting case. Yeah, detecting fake reviews. There's probably a sense in which now we have superhuman performance. It's a very complicated social thing though. So what you just said is that people are easily tricked. But actually there's some evidence that young people like you have become so skeptical that you're tricked in the other direction, that you very often diagnose real news as fake because you're kind of braced for an onslaught of fake news, which you're mostly actually not seeing. They're targeting different demographics with that kind of fake news. Before I move on here to this final part, I just want to emphasize that these are all interesting tasks, but they are not the tasks that you would sign up for if you took a class in NLP or like natural language understanding. There's no sense in which question answering is on this list, or natural language inference, or summarization, right? These are all more mundane kind of nuts and bolts tasks, and I think that's important. Yeah?
Is it like one of those tasks can make the other task like not useful, let's say like autocomplete. So if everybody is using autocomplete, then authorship detection will become like right.
Because we'll all be just Google.
Google, yeah,
That's
doing
right.
that.
It certainly could happen, yeah. I'm trying to think, have there been things that we used to do that have been made obsolete beyond just like people being good at spelling? Maybe you don't bother because spell check is so good. Yeah. This third part here, now we're going to go down to earth. Performance at or above humans only in controlled environments with specific metrics. I want to give you a sense for what I mean by that, but first I want to preface this with saying that you might think that the ultimate test of systems like NLP systems would be the Turing test. Right? People have heard of the Turing test before. This is the idea that a system could be counted as intelligent along the dimensions that we care about if in just text-based interactions with a human, it could trick that human into thinking that it was itself a human. So kind of like successful impersonation of a human in this very restricted way that you're just communicating with text, and the entire emphasis is on dialogue. And so you might think that that's the way we're going to evaluate NLP systems. That'll be the gold standard. The field figured out pretty quickly that that's a complete non-starter. Two examples of that. So the first, this is the statement of the Turing test. And let me the results from the first real Turing test, which was run in 1994, and they still are run. This is just funny quotes from it. Cynthia Clay, the Shakespeare aficionado, was thrice misclassified as a computer. At least one of the judges made her classifications on the premise that no human would have that amount of knowledge of Shakespeare. Lizette Gozo was honored as the most human of the agents for her discussion of women's clothing, although one judge rated 2 computer programs above her. That's kind of a lot of interesting things happening there. So on the one hand, this assumption that people couldn't have kind of encyclopedic knowledge of a thing. On the other hand, I suspect that in this discussion of women's clothing, that's kind of stereotyping of women, and that's like benefiting these systems, right? Although it should be said, 2 computer programs were rated above her. And then here's a more recent case, the case of Eugene Gustman. So this was another Turing test that happened about 10 years ago, I think, about 2014. A computer program called Eugene Gustman, which simulates a 13-year-old Ukrainian boy, is said to have passed the Turing test at an event organized by the University of Reading. So the location is important there, because the reason that people thought Eugene Gustman was, it's a computer program, the reason they thought it was a human is in part because in being a 13-year-old Ukrainian boy, interacting with people in the UK, all his disfluencies and his bad attitude were attributed to the fact that he's Ukrainian and a teenager. And so in that way, they could make up for lots of failings of the system, and people were tricked, right? It's easy to see how an untrained judge might mistake wit for reality. But once you have an understanding of how the system works, the misdirection and deflection, that is his disfluencies and his hostility, become obvious. But the point here is that for the Turing test, people are really easily fooled. And actually, now that I've mentioned this, you might now encounter moments in your life where you're not sure whether you're passing or failing a Turing test. This can happen now in customer service interactions where you can't tell whether it's a fully automated system or a human guiding with some canned responses or a real human. And this will lead you probably eventually to, in a very insulting way, ask somebody whether they're a human or a computer, and the person will be aghast or not, depending on what the truth is. So we don't do Turing tests. What we do, and here are what I'll call standard evaluations. This is common throughout artificial intelligence and NLP. So we create a data set from a single process. Like you could crowdsource a bunch of labels or harvest some information from the web. The point is that it's a single process. You divide it into disjoint train and test sets, and you set the test set aside. You're not going to look at it. You develop a system just on the training set, and then only after all your system development is complete, you evaluate it on that test set that you've held out, and you report those results just as they come in. And the idea there is that in holding out that test set, you're getting a look at what your system's capacity is to really generalize to new data. But because of one here, you can see that this is likely to overstate the performance of these systems. Because one is saying that all this data is homogeneous. That's not the way the world works. You did this split here and you didn't look anymore, but you kind of have a lot of guarantees about consistency. So your performance on this held out set, it's not quite been held out. It's not quite pristine if we have real world goals, for example. And the way that the fragility of this has emerged, the way it's being so generous to these systems, that's really emerged with the arrival of adversarial testing. So one of the first famous cases of this concerns the SQUAD data set, the Stanford question answering data set. Just briefly, the system is given a passage like this from Wikipedia and a question, and the goal is to come up with an answer. Really influential task. And the relevance of this for the current section is that for SQUAD 1.1, which is an early version of SQUAD, a couple of years ago, we saw human performance surpassed. So humans are at 82.3 or 91.2 there for the F1. We could concentrate on that metric. That's a standard classifier metric. And this BERT ensemble, just from last year, I guess, finally surpassed human performance. And that was reported as this task being solved and as humans having achieved superhuman performance at question answering. And that's the sense in which you might think, oh wow, real progress. However, the same authors that released SQUAD released an adversarial testing set for it. And the way that works is, let me get to them. You just systematically perturb examples from the training data to generate a test set by appending a misleading sentence. That's the adversarial test. So the way that works is, this is the original case here with the passage, the question, and the answer. The adversarial thing is to just insert onto the end, quarterback Jeff Dean had jersey number 37 in Champ Bowl. It's sort of written by a crowd worker with some prompts, and it's designed, obviously, to be confusing with regard to the real answer, which is expressed just up here. And lo and behold, systems predict Jeff Dean. They're fooled by that adversarial sentence. And it had devastating effects. One of the clever things about SQUAD is that it's hosted on this central platform where you upload your entire system and it's evaluated in there. And so when this team released SQUAD 2.0, which has these adversarial examples in it, they could rerun everybody's system and look at how the numbers changed. And the striking thing about how the leaderboard changed is not just that everybody's performance dropped. You might expect that because they had made the testing set deliberately harder. It's that it was also shuffled. So it's not like the top systems all kept their original places. Everything was kind of chaotic, reflecting the fact that especially those top performing systems, they had found pretty brittle solutions to this problem. And they were therefore very susceptible to the adversarial testing. You might think, wait a second, the adversarial test was just to append these new sentences. Why don't I just train on those data, right? And then I'll have a more powerful training set and I'll be attuned to this trick that you're pulling on me. However, what if you prepend them? And they did that too. So you train on the augmented appending versions, which have the extra sentences, but now you put the misleading sentences at the front. And lo and behold, systems are tricked in the same way. And you might think, okay, well, I'll train on this expanded test set or training set too. But then I can test by putting them in the middle somewhere. And then you might say, well, I'll train on those sentences as well. We can keep going back and forth like this. And the worrisome thing about the way NLP is working right now is that we can go back and forth like that forever. I think unlike in computer vision, where this kind of adversarial back and forth has led to more robust systems, in NLP, it's just like you continually do this thing of whatever clever thing you did, I can match it with some adversarial testing examples that you fall down on. Let me show you one more example of this. Yeah, Andrew?
So why do you think NLP models are so brittle to this adversarial testing when computer vision models are not as brittle?
I don't have a deep answer to that. I mean, I think a lot of work could be done on that. I would just start with the observation that the underlying data are so different. You know, language is like discrete. It's got all these lexical items. It's structured in a very particular and symbolic way, whereas the computer vision problems are much more unstructured. Yeah, but we'll see. But I don't know what to make of that and why that's causing these differences. It could also be that NLPers are just better at this kind of adversarial testing, and therefore we're exposing the problems more quickly. Let me show you one other one, just because this is kind of an interesting moment for this task. So natural language inference is another one of these big tasks in NLP, meant to key into kind of common sense reasoning, another core capability for humans. You're given a premise, which could be a word or a full sentence, and a hypothesis, and you have to guess the relationship that holds between them, which could be entails, contradicts, or is neutral. It should mean like that they're both consistent with each other. There are a couple of major NLI data sets. So SNLI, the premises are image captions, and the hypotheses were written by crowd workers. It's very large, 550,000 training examples, 10K dev and 10K test. Sam Bowman was the lead author on that, and he also was behind multi-NLI, which is very similar to SNLI, but now the premises are drawn from multiple genres. And the hypothesis, again, written by crowd workers. What's interesting about this one is this semi-adversarial mismatch test condition. So in the match condition, when you do your testing evaluation, you do that on genres of text that you've seen before. In the mismatched version, you test on completely new genres. And that's a kind of adversarial thing to see how much they're actually generalizing beyond what they've seen. And the mismatch condition can be really serious. Like you might have trained on a bunch of books from Project Gutenberg and tested on the 9/11 report. So really seeing how these systems generalize. I think that's very interesting. And the final one is the Winograd NLI, which is embedded in the GLUE benchmark, which is a whole bunch of tasks. These are very challenging examples, originally created by Terry Winograd, that are designed to stress test, especially NLP systems that are depending on statistical regularities. It's small, but human performance is outstanding, and these have proven very difficult for NLP systems. Yeah?
Are these data sets available for anybody to train in machine learning?
Absolutely, yeah. That's another, I mean, NLP is wonderful about openness with data and code. So we released SNLI, Sam released multi-NLI, then Sam Bowman, he's also part of the GLUE benchmark, which is a whole framework for evaluating systems on lots of tasks. And that's why it's an exciting moment, because this is all out there and a lot of people are working on them. Here are some Winograd sentences. I stuck a pin through a carrot. When I pulled the pin out, it had a hole. The carrot had a hole. It's kind of testing to see whether or not you can do the proper kind of anaphora resolution and also reason physically about the objects. Right? The table won't fit through the doorway because it's too narrow. The doorway is too narrow, not the table is too narrow. Right? So you have to do a kind of mental simulation to get that one right. Have we achieved superhuman performance on these tasks? You know that this is just going to be in the sense of we have a computer, say, calculating an F1 classification score, you know, like something like accuracy, and then we'll force a bunch of humans to do that same task, which is not a human task, but we'll force a bunch of humans to do it, and we'll have superhuman performance if the system beats the human at that weird thing. Not that these systems are better at reasoning in natural language, right? I'm trying to be very careful about what we mean by superhuman performance. So human agreement level estimated at 91.2 in that weird way I just described. 2 papers in 2019 reported scores that are above that, superhuman. For multi-NLI, human agreement is about 92.6, basically the same as SNLI. The best systems are around 86% for both matched and mismatched. So maybe we'll see an announcement about superhuman performance any day now. For Winograd NLI, this is again more interesting. Human agreement is estimated to be about 95% because it's a small, curated, high-quality data set. After years without progress, and what I mean by that is that standardly when people entered competitions that had this data set as part of them, they would just report chance rates in fear that their system would do worse than chance on that data set. So a little bit of a cheat, and it meant that there was like no progress for a long time. However, scores above 90% were reported just in the last few months. So you can be sure that somebody's going to hit close to this 95 probably before the year is out. Is that going to be a fundamental breakthrough in NLP and artificial intelligence, or is it going to be a kind of brittle solution that we can easily adversarially destroy? My guess is the latter. Let me just give you a sense for what these adversarial testing things are like. So this is a nice paper where what they do is they just go through the NLI examples and replace, for example, phrases like saxophone with phrases like instrument. So things that are more general or more specific. And they can do that at scale because they have a guarantee that kind of replacing a specific with a more general term will, for example, preserve the entailment relationships. And so they just go through and create all these new examples that are in the vocabulary of SNLI, so we know that the system has seen those words, but it's never seen precisely these examples. It's a very generous adversarial test. It almost seems friendly, and yet systems do very badly at these new cases. Again, exposing that they have kind of brittle solutions. This is a similar paper where they just take examples and systematically transform them in ways that humans know will preserve or change meaning in a certain specific way. And you might think if the system has really learned to reason, it will be able to do that same very human thing, but in fact, systems fall down on these new examples. Even though it's vocabulary they've seen and example types that they've seen before, they're just not doing the kind of deep analysis that gives them guarantees about out-of-domain examples like this. That's another paper that does that same thing. So let me just wrap up here and then we can have some open discussion. First, I want to emphasize that in NLP, people are now obsessed with the brittleness of these solutions, and there's lots of adversarial testing happened. So if you want to find out more about this, there's first of all a lovely paper by Levesque on our best behavior, and it's kind of about how we should do more stress testing of our systems. And it has this nice Blade Runner style question: should baseball players be allowed to glue small wings onto their caps? Which I think the idea is that humans have an immediate answer, but this could be very confusing for an artificial agent. More down to earth, there's like some big NLP workshops that are focused on this question of how we avoid black box solutions and how we find examples that are going to push our systems in useful directions. So it's kind of an exciting time because the big push for doing a lot of deep learning, for example, in NLP, is now being counterbalanced by people's hard-nosed, realistic looks at what these systems are actually capable of doing. So let me just wrap up here. So first, I just want to summarize. There are areas of AI in which we have systems that achieve perfection, or at least genuinely superhuman performance. And there are language tasks where we see that level of performance, like spell check, information retrieval, and language identification. But they're not yet tasks that we closely associate with human language use, like question answering and common sense reasoning. For those things, those really meaty problems, tasks are solved only in that very narrow sense that we force some humans to do one weird, unnatural thing and compare them against what computers are set up to do well on a very specific data set with no guarantees that that behavior will generalize outside of that data set. And in fact, adversarial testing is showing that very, very often it doesn't generalize in those ways. Thank you. I have a couple of minutes for questions if people have any questions. Yeah.
Do you think that study of biology, study of like neurons in the brain will help us like solve some of these more abstract problems?
I really do. Yeah, I mean, I'm biased. Like, I'm a linguist and cognitive scientist, and so I kind of think, like, look, humans are the best language learners possibly in the universe, but certainly known to us. And so to the extent that we can understand their behaviors, that is very likely to inform the next generation of systems. And I'm feeling this happening also, so like now there's a push toward like zero or few shot learning. This would be that instead of bragging that I needed 100 million examples to train my system, I would say, well, actually, I can show you some interesting behaviors with just 2 or 3, which is something that humans do very routinely. Sometimes if I just tell you what the rule is, having seen no data, you can then apply it. And that kind of thing, I think, is going to be really inspiring for the next generation of AI systems. Yeah.
Considering how brittle some of the NLP solutions you've shown are, you're just sort of like bringing it to like non-NLP stuff as well. Do you think there should be some human oversight in like the machine learning solutions that are deployed, like sort of worldwide, to kind of scale up if it's a brittle solution like that? Then there could be some.
I think it's a great point. Yeah, should there be human supervision? I mean, I kind of want to say yes. I would want to say I don't think it's particular to NLP, and I did show you that case of the panda and the nematode and the gibbon, and that was exposing a brittle solution there. I guess what it's going to come down to, if we follow through on what you're thinking, is like, then we need explainable NLP systems. They need to be able to articulate for us why they're behaving in the ways that they do so that we can properly kind of monitor them. And that's yet again another exciting frontier for AI, I would say. And that's kind of what that, getting beyond black boxism and towards systems that we can actually introspect about, I think that'll be a big part of it. Yeah, well, Edwin, go ahead.
Yeah, so my question is about machine translation right now. So what systems do is like do parallel corpus and they match with it. So my question is it possible that if we don't have parallel corpus, can we learn machine translation? Suppose take an example, like we have some older languages and we have developed that languages and we are speaking its replicated languages right now. Can we match those languages with machine translation?
For the first part of your question, I can just say that there's really exciting research happening in MT that doesn't involve parallel corpora, and a lot of it is coming out of Facebook. And they are, so for the second part, is the second part kind of about languages where we don't have as much data? Was that, or maybe I missed what you were saying?
For the languages which we have a lot of data, but we don't know it semantically right now.
I think, all I can say is that I think you're right to connect those two problems, because I think for like kind of what they call low resource languages where we don't have massive corpora, we can't expect to have aligned corpora for them. And so what we need to do is figure out solutions that can depend on the data that we have and also depend on the other translations that we can do to kind of help them, support them in the more challenging low resource setting. And again, there's lots of stuff happening in that area now. But getting back to the question that came before this, it's very unhuman. And so maybe this is kind of like, what's the metaphor? Like, we want to get to the moon, so we build a taller ladder. And you might think that to really solve these problems, we need to think, like, be inspired by human learners, for example, and human translators.
Actually, remember that when you look at the retinal scan, we can see the gender. So it's kind of like chickens, I'd say, where you look, when they're born, like as soon as they hatch, they need to be separated based on, because they have different diets. So humans are kind of trained like how the machines are trained, where they guess, is this a male or female? And then by the end of the training process, they can actually just like look at the chicken's video and and they guess the gender just when it's a baby chicken. So maybe if we train doctors in a similar way where they guess based on the retinal scans, and if after a certain training they're able to guess the gender, then we can get a better comparison on whether that's just got to do with the data itself or it's actually possible to.
That's wonderful. Yeah. But do we have superhuman performance for AI systems that do chicken gendering? It seems like the sort of thing where we might, because there's an economic incentive. Yeah. Andrew.
Thank you so much for your talk. For those of us who are inspired by your talk and now really want to work on NLP projects, but maybe they're beginners in NLP, what do you recommend as how people can get started in these type of really interesting projects?
Well, it's a great area to work in because there are lots of great materials online, courses that you can take, and like Python notebooks that you can use to experiment. There's lots of data because of NLP really having moved to an open science kind of philosophy. So like data and code, or it didn't happen, right? This emerging as a philosophy. So there's lots of stuff out there that could empower you. And then the other thing I would say that kind of connects directly with this lecture is the adversarial testing thing is exciting because you could make a contribution just by exposing a flaw in an existing system that people thought was really good. Now, just to expose the flaw, given what I said here, that's going to be easy, right? You'll find a flaw. But the creative part would be to find a flaw that we could understand or that we could address somehow. And that doesn't require huge compute resources. It doesn't mean that you're heating your apartment with a deep learning system, like I think Andrew sometimes does. It just means being really thoughtful about the data. And then the other part about that is that as you kind of explore in that adversarial way, you might hit on some modeling ideas that will address those problems, and then you've kind of got a full-fledged project in the works. And so that's like, I guess I ended mainly on bad news. I tried to sound like an optimist. But for the research side, I think it's a really exciting time. Yeah.
Do you think NLP's fundamentals are correct, or is that a part of the causation for the brittleness of the solutions?
That's a great question. I don't know. It kind of gets back to your question, like, if you believe that we should take our cues from humans, then we're really off the mark, because no human has ever learned anything about language by just being put in a room with a huge amount of text. The way humans learn language is a complex social process. It's multimodal. Babies are really like big data machines. Lots of sensory experience, lots of their own simulation, but it's not that they experience a lot of language even. And so if we wanted to take our cues in that way, we'd be designing very different systems and using very different data sets to push these systems forward. And the other thing I would say is probably current deep learning systems need more structure. They need to have at least some capacity to do what humans do so well, which is like learn from a rule that I just state for you. You can pack a huge amount of information into a conditional like if P then Q that could take massive amounts of data for a system to learn, and even then it might not have learned it in the robust way that you could learn it if I just told it to you. So maybe bringing in capabilities like that would also lead to a phase change in system performance.
All right, we're just about out of time, so let's give Dr. Chris Potts another big round of applause. Oh, and for those of you who are interested in being official members for ML at SJSU and be hosted on our website, we do track attendance. So I'm just going to put up the attendance link really quick. If you guys are interested, you can fill out the name there. And then if anyone is interested in joining Dr. Chris Potts and us afterwards for dinner to get to know him a little better, please stick around.
Being an NLP engineer? Oh, absolutely, yeah. Yeah, that's a hot area. Yeah, all the tech companies. Yeah, and then like you can also there's like whole industries that aren't yet taking advantage of language data in the way they could. Like one that I know pretty well, some work I do with a startup is healthcare. Generates a huge amount of text. Experts currently review it, and they can be helped by AI systems. And that implies that they need to hire a lot of NLP